Okay guys, let's talk some more about limits. Today in lesson 11.2, we're going to talk about finding limits using properties of those limits. But first, let's kind of pick up where we left off in 11.1, where we were evaluating limits by looking at graphs. So here we have a limit to find. The limit is x approaches 2 of this function, which is graphed right here. So we're trying to find the limit as x approaches 2, so as I get closer and closer to an x value of 2 from both sides. As I approach 2 from the left, notice I'm coming up here. I'm getting closer and closer to this point right here. As I approach 2 from the right, well, I'm coming down on this part, I'm getting closer and closer to this x value, or I'm sorry, this y value right here, this point right here on my function. So as I get close to an x value of 2 on my graph, my y value is getting very, very close to 3. So what I want you to notice about this function is that it is continuous at x equals 2. We're going to talk a lot more about continuity in lesson 11.3, but notice right here that I could draw right through this point where x equals 2 without picking up my pencil, or my pen in this case. So as I approach from the left and I approach from the right, that limit is the same thing as the very value of the function right there. So if we're talking about a function where it's continuous at this x value, where I'm trying to find the limit, I can actually evaluate the limit by just finding the value of the function at this x value, in this case x equals 2, which means I'm directly substituting. I'm saying where x equals 2, what does this equal? Well, 2 squared minus 2 times 2 plus 3. And if I do that, 2 squared is 4. Minus 2 times 2 is 4. 4 minus 4 plus 3 does give me 3. So the nice thing is if we're trying to evaluate if we're trying to evaluate a limit of a function that we know will be continuous, then we can just do it by direct substitution. So if I'm finding a limit in a case like a polynomial, remember that polynomials have smooth, continuous curves. We learned that in Algebra 2. We reviewed it again at the beginning of the year in this class. So if it's a polynomial, we can find the limit as x approaches a of our function by just evaluating f of a, literally taking this value right here and plugging it into my function and evaluating. So we can evaluate by direct substitution. Polynomials are not the only functions we can do that for. We can also do that for power functions. So where I see a polynomial raised to a power, it'll work there. So I can see here if the limit as x approaches 2, just plug 2 in. See what I get. And a radical function, so where the whole thing is inside, the whole polynomial is inside a radical. So here, I'm literally just plugging -2 in for my x value and evaluating by direct substitution. So there are lots of cases where we can just straight up plug in that x value that we're trying to find the limit as we are approaching. So it's also true for rational functions. Remember, rational functions, ratios are fractions, so these are quotients, as long as that direct substitution doesn't cause the denominator to become 0. So in this case, notice if I plug in 2 for all the x's on the top and the bottom, I get -3/1 or -3. So as long as it doesn't cause my denominator to go to 0, then it's okay to evaluate just by direct substitution. If it did cause my denominator to go to 0, I know that would be a problem because I'm not allowed to divide things by 0. That would be undefined. It's what we call an indeterminate form. It tells me I can't determine the limit by just plugging in that x value because of that trouble spot it gave me in the denominator. And we'll talk about how to handle that in a couple minutes. First, let's talk about some general properties here of limits. First, a couple of actually basic limits. So first, the limit of a constant function. A constant function is like y equals 3, or y equals 16, y equals a constant value. So y equals a number is a horizontal line, right, through whatever that constant value is. So if I think about the value here as x approaches 0, well, as I approach 0 from the left and the right, the value of my function is whatever this constant c is. Or if I'm over here at like x equals 5 and I approach from the left and right, what's the value of my function? The y value again is still just c. So no matter where I'm looking for the limit as x approaches any x value of a constant function called c is just equal to c. So for example, right here where I have the constant function y equals 4, a horizontal line through 4, The limit as x approaches 2. As I approach 2 from both the left and the right here, I can see that I'm getting very, very close to an x value of 4, or a y value of 4 rather, because my y value is always 4. So no matter, if there's no variable in here, no matter what x value I'm approaching, the limit's always just that constant value. Another basic limit that we should know is the limit of an identity function. The identity function, something that is popped up in algebra for us, is the function y equals x. That's a line, right? Because x is to the first power, y is to the first power. If I think y equals mx plus b, then we're crossing at the origin right here, a y-intercept at the origin, a slope of 1, so that's a diagonal line at like a 45-degree angle through quadrants 1 and 3. So if I think about, for example, the limit as x approaches 3, as I get close to an x value of 3 from either side, so I'm like this on my function, closer and closer to x equals 3, my y value is getting close to 3 as well. So here I see again this idea that direct substitution will work. If I plug in 3 for the x value here, I get just 3. Direct substitution works for this constant value too. If I think about plugging in this 2 for any x I see up here, oh hey, there aren't any x's, so I just get 4, right? So that same idea of direct substitution still works. Okay, so now some basic properties of limits. Now, we won't have to use these properties very frequently in the work that we see in this lesson. We will have to use these properties regularly when we start to evaluate limits in calculus, which a lot of us are headed toward next year, or maybe at some point in a college course. So it's important to understand more than one way of taking a limit. So first of all, the limit of a sum or a difference. So if I have the limit as x approaches a of two different functions, one called f of x, one called g of x, which are added or subtracted, well, that's the limit of the first function plus or minus the limit of the back function here. Well, that's nice. So we can see, for example, in the work that we've done, maybe if I have the limit as x approaches 5 of x plus 7. So I know I can do direct substitution in here, but let's see that this sum formula or sum property works for the limit as well. So I can break this up. The limit as x equals 5, the limit as x approaches 5 of x plus the limit as x approaches 5 of 7. So I split up those terms and take the limit of each one separately. So here, the limit as x approaches 5 of x, I'm going to use direct substitution, and I'm going to remember that that's the identity function, and I get that 5 that I plugged in. Here it's a constant function. The limit, no matter what x value I'm approaching, of just 7 is 7. So I get 5 plus 7 is 13. That's the same thing that we would get if we directly substitute from the beginning. Some of you are thinking like, why is it worth it to think about splitting this apart? The reason it's important is when we see applications of limits as we move next into our calculus courses, what'll happen is they'll say like, find the limit as x approaches 2 of f of x plus g of x, but f of x will be like some graph that I have to read, and g of x will be like a table, or f of x will be an equation, and g of x will be a graph. So I'll have to work with these two different functions as they appear in different representations. So it's important to know that we can split that up and just take the limit of each one of these separately and then add or subtract. So in a very similar way, the limit of a product, so if I'm multiplying f of x times g of x and then taking the limit as x approaches a, it's the same as taking the limit of this first function times the limit of the back function. So in an example for what we've seen here, if I have the limit of 6 times x, see the multiplication in there, right? I can think of it as the limit as we approach 5 of 6 times the limit of x as we approach 5. So here, the limit of 6 as we approach 5, that's a constant function, so it's just 6. The limit of x as x approaches 5, I'm going to directly substitute in there and get 5. So 6 times 5 gives me 30. That's, of course, the same thing that we get if we directly substitute that 5 from the beginning. It's just important to understand that we're allowed to split up that product and take the limit of each one separately so that in the future, when we see f of x and g of x in different representations, mixed media there, kind of where we get tables and graphs and such, that we'll be able to split it apart. Okay, so another limit of a product, suppose that suppose that the product I have is a constant value times a function, a scalar product. It's actually the same to multiply that scalar to the function first and then take the limit as it would be to take the limit of the function and then multiply it by that constant value. So I can think of this as taking the limit of the function and then multiplying by c on the outside. So for example, just the same as the one above right here. Notice that we had 6, which is a constant multiplier, times x, which is like a function. So instead of evaluating this 6 times x together, I can say, well, since this 6 is a constant multiplier, I can just pull it on out front and call it 6 times and take the limit of just that function x, which I would do by direct substitution. So I get 6 times this value right here gives me 5, which gives me 30. Again, an important rule for what we will see applied in lots of ways in calculus. All right, one more property. So we talked about addition, subtraction, multiplication. Let's mention division. We actually talked a little bit about this a minute ago when we talked about rational functions. So the limit as x approaches a of a function f of x divided by g of x is the limit of the numerator divided by the limit of the denominator, provided that doing that, taking that limit in the denominator does not give us 0, because we know that we're not allowed to divide by 0, right? So here I can take the limit of this function by taking the limit of the, what is the matter, Kenai? Guys, I have fed her, I've walked her, I've taken her outside, I've given her hugs. I don't know what she wants. This is my life all day long, every day. She's such a howler. Okay, so here I can try taking the limit of the top and the limit of the bottom. If I get 0 on the bottom, then I'll have to have another strategy. So I take the limit of the top, directly substitute, it gives me 5. Take the limit of the bottom, directly substitute that 1, it gives me -3. Perfect, nothing weird happens there. I'm allowed to say that that limit is -5/3 just by direct substitution. Let me see what, you think I can, what's gonna make you happy, Kenai? Guys, let me try to make her happy. Guys, she wanted to go outside, but she wanted me to escort her. My backyard, I get these blue jays out there and they are so mean, and they dive bomb her and try to chase her out of her own backyard. Poor girl just wants to poop in peace. Can an old girl get that? Okay. All right. So we've been talking about just most of the time it's okay to find these limits by direct substitution, but when does that not work out? When's that not okay? So we've already talked about one case, and that's a rational function dividing where direct substitution makes that denominator equal to 0. So if we try direct substitution and it gives us a 0 in the denominator, how do we handle it? So we've got a couple of ways we can do it. So let's take a look at this particular example. The limit as x approaches 3 of x squared minus x minus 6 over x minus 3. We see that plugging this 3 into the denominator would make it go to 0, right? It also makes the numerator go to 0, but that's not a problem. We're allowed to have 0 in the numerator, but that 0 in the denominator is a problem. We mentioned this a minute ago. Getting 0 in the denominator is called an indeterminate form. Indeterminate, as in we cannot determine the limit that way. So we have to have another method. Understand, this does not mean that the limit equals 0. This does not mean that the limit doesn't exist. It simply means that we cannot take the limit using that method of direct substitution. So we have to have some other way to go about it. So the idea is I need some other way to rewrite this so that it has the same value, the function, the equation has the same value, only it's written in a way that doesn't give me 0 in the denominator. So we did this when we were dealing with rational functions in Algebra 2 and earlier in our course. We're just trying to change how that fraction looks. So the first thing we could try is just factoring and seeing if we can cancel out a common factor on the top and the bottom. With this particular example we were just looking at, that works out really well. If I factor this numerator, I get x minus 3 times x plus 2. That x minus 3 on the top and the bottom cancels out. So this is the same thing as saying the limit as x approaches 3 of that x plus 2. That x minus 3 on the top and the bottom, we know that that means that our function has a hole at x equals 3, but it doesn't matter that the function has a hole there. If we're trying to evaluate the limit, I only care about what I'm getting close to as I approach from the left and right hand sides of x equals 3. I don't care what happens at x equals 3, so I don't care about that hole. So once I get this rewritten, now I can try direct substitution, plug that 3 in there, 3 plus 2, 5, perfect. Okay. So sometimes factoring and canceling will help us out. Why don't you give this one a try, just like a whiteboard problem that we would do in the classroom. So pause your video here, try it, come back in a minute, and we'll work through it together. Okay, so hopefully you've tried it and come back. You're looking to see if you can factor and cancel in a way that you can rewrite this and then it's not going to have an indeterminate form. Oh, actually first, I hope you tried direct substitution. If I plug 1 into the denominator, I get 0, right? If I plug it into the numerator, I don't know what I get. I don't care. That 0 on the bottom is a problem. So I always want to try direct substitution first. Since that won't work, let me try factoring next. So my numerator can factor, let's see, x is in the front. It's got to be 1 and 3, or 3 is going to be positive, or 1's going to be negative. Oh, look, those x minus 1's cancel on the top and the bottom. So this will give us the same value as the limit as x approaches 1 of just x plus 3. So now I can try direct substitution again. Just plug that 1 in for x. 1 plus 3 gives me 4. Okay, so let's talk about some other cases where factoring won't help us out. So if I try direct substitution and it gives me the indeterminate form, then I try factoring that fraction. If it's not factorable, or if factoring doesn't lead me anywhere, the next thing I should think is there a binomial happening in that fraction where I can multiply by a conjugate? And we see this happening very often where I've got radicals in my function, and rationalizing that radical part can be very helpful. So we remember from Algebra 2 that I rationalize a radical part by multiplying by its conjugate. Okay, so in this particular problem, first I try direct substitution. Look, 0 on the bottom, right? That's the indeterminate form. I cannot determine the value of the limit that way. I have to try something else. So then I think, can I factor that? Oh boy, I don't know how to factor that on the top, right? So factoring fails us there. So let's try this strategy of multiplying by a conjugate. So I see in the numerator, this happens again a lot where I see radical parts. This is a trick that can be especially helpful. So I see this binomial, this radical part minus 2. So I'm going to try multiplying that numerator and denominator by the conjugate of this binomial up here, which will be the square root of x, the square root of 4 plus x plus 2 instead of a minus right there. Okay, so the conjugate right here, I just changed that term, that sign in between these two terms, that minus sign I changed to a plus sign, that's the conjugate. If I multiply to the top, I have to multiply to the bottom, right? Okay, so now in my numerator, I have to FOIL these. Remember when we're multiplying conjugates, the inner and outer terms cancel out. So as I FOIL this, I only actually have to worry about the first and last, not inner and outer. So my first term, the square root of 4 plus x times the square root of 4 plus x is the square root of 4 plus x squared, or just 4 plus x. Inner and outer cancel out. My last term, negative 2 times positive 2 is negative 4. On the bottom, I'm going to leave this x factored out. I'm not going to distribute it in. Remember that this factor of x in the denominator means that when I plug in 0 here, I get 0 as a denominator. So ideally, I'll get this x to cancel out. So I want to leave it factored out, hoping that it'll cancel in the numerator. So I have x times the quantity, square root of 4 plus x plus 2. Look up here in the numerator. Positive 4 and negative 4 will cancel out, right? Okay, so now this is the same as saying the limit as x approaches 0 of x over x times the square root of 4 plus x plus 2. Oh, look, those x's on the top and the bottom cancel. So now I don't have to worry about plugging x or plugging 0 in there and 0 times this stuff becoming 0 because I don't have that x as a factor anymore. So in my numerator, notice everything cancels out, which means I've got 1 as a numerator now. So I have the limit as x approaches 0 of 1 over the square root of 4 plus x plus 2. Realize that everything that we've done right here is algebra. I'm just rewriting this fraction so that it looks different than the original fraction, but still has the same value. So now when I plug in x equals 0 here, it'll give me the same value for a function. I just won't get that 0 in the denominator. So, or I should say, this function is equivalent to this function. It's just rewritten in such a way that I won't get 0 in the denominator anymore. So now when I plug in 0, I get 1 over the square root of 4 plus 0, that's just 4, plus 2. That's 1 over 2 plus 2, or 1/4. So that's another strategy. In general, we're just trying to rewrite these fractions with any plan we have, any strategy, and we learn several in Algebra 2 in such a way that it just looks different than the original. So why don't you give this one a try like a whiteboard problem? So pause here, give it a try, come back, and we'll go over it together. Okay, so hopefully the first thing you tried was direct substitution, and you saw that plugging in 0 right there for that x gives you 0 in the bottom. That's the indeterminate form, which means that I cannot determine the value by just directly substituting. Have to try another trick. So the next trick we learned was factoring. Can I factor this? Wait, I don't know how to factor that. Okay, so now I'll use this trick of trying to multiply by a conjugate and see if I can get this looking different. So the conjugate of this numerator is the square root of 9 plus x plus 3. So I multiply that on the top and the bottom. So now, this is equivalent to the limit as x approaches 0 of this denominator. I'm going to keep it x times this quantity. In the numerator, I'm going to FOIL these together and see what I get. The square root of 9 plus x times the square root of 9 plus x is 9 plus x. Because we're talking conjugates here, the inner and outer cancel each other out. My last term, negative 3 times positive 3 is negative 9. So now I see those 9s cancel out, right? Positive and negative. So now I have the limit as x approaches 0 of x over x times the square root of 9 plus x plus 3. And now I see those x's cancel on the top and the bottom, leaving me just 1 in the numerator here. So what I'm going to evaluate now is the limit as x approaches 0 of 1 over the square root of 9 plus x plus 3. So now I'm going to try that direct substitution again now that I've rearranged this so that it looks different. So when I plug in 0, my numerator is still 1. My denominator is the square root of 9 plus 0 is 9 plus 3, or 1 over 3 plus 3 gives me 1/6. Again here, we're using any trick we know, like factoring or multiplying by a conjugate, but any trick we know to rewrite a fraction so that it'll look different but be equivalent to the original fraction. So we could also use techniques like combining like terms, like rewriting complex fractions. If we have a fraction inside of a fraction, you'll see a problem like this on your homework. If you have fractions inside of fractions, then I want to simplify my numerator to be one fraction, simplify my denominator to be one fraction, and then think the numerator divided by the denominator is the same thing as the numerator times the reciprocal of the denominator. So complex fractions like we saw in Algebra 2. Okay, so we said try direct substitution first. Then we said, where is direct substitution not going to work out? So the first thing we said was it's not going to work out if I have a rational function, so a fraction where the denominator goes to 0. We just had a couple of examples of how to handle that. So where else will direct substitution not work out? Well, it's not going to be quite so clear how it works if I have a piecewise function. So where else can we not just direct substitute? Piecewise function. So here's one. Suppose that I'm trying to take the limit as x approaches 2 of the function f of x, where f of x is this piecewise function. Notice that x approaching 2, that is the breaking point where I jump from one piece to another. If 2 wasn't this breaking point right here, if I was looking like x approaches negative 3, where it's not going to jump from one piece to the other, it's okay because I'd just be on this piece of the function, right? And that's a continuous function, that's a polynomial, so I could just plug in. But I'm worried about the fact that 2 is this place where I change from one piece to the next. So because x equals 2 is the value where we change from one piece of the function to the next, it's possible that we have some break or skip or jump there. So to find the limit, we have to do is compare the left and right limits and make sure that they are equal to each other. If the left and right hand limits are equal to each other, then that is the limit. So that's our strategy. Check the left hand limit and the right hand limit, see if they are the same. Okay, so let's do that. Let's check left and right hand limits. So the left-hand limit, the limit as x approaches 2 from the left of this function. So if I'm looking at numbers to the left of 2 on a number line, those are numbers smaller than 2, right? Less than 2. So I'm on this top piece of the function. So what I'll do is plug 2 in on the equation for this top piece. So I get 2 squared plus 5, or 9. That's the left-hand limit. Let's look at the right-hand limit. Zoom it out a little bit here. Okay, so the limit as x approaches 2 from the right. Well, if my values are to the right of 2 on a number line, then they're greater than 2, which means I'm on this piece of the function. So I'll plug 2 in here. 3 times 2 plus 1 gives me 7. So the left-hand limit is 9, and the right-hand limit is 7. So from the left, I'm coming in at 9. From the right, I'm coming in at 7. Those aren't going to match up, right? So that I don't have a limit there because I'm approaching 2 different values from the left and the right. So because the limit as x approaches 2 from the left is not equal to the limit as x approaches 2 from the right, the limit as x approaches 2 does not exist. Let's try one. And by let's, I mean you try one. So try this one just like you would for a whiteboard problem. I would like you to find the limit as x approaches -1 on this piecewise function. Okay, so I hope that you're noticing here that -1 is the x value where I jump from one piece to another. So I have to carefully investigate the left and right hand limits. So the limit as x approaches -1 from the left on this function. So values to the left of -1, they're x values that are less than -1. So I'm talking about this piece of the function up here. So that's just -1, right? And then on the bottom, the limit as x approaches -1 from the right on f of x is equal to the cube root of 2 times -1 plus 1. That's the cube root of, this is going to give me -2 plus 1. That's the cube root of -1. What's the cube root of -1? -1. So I see that the left-hand limit and the right-hand limit are the same, which means that it has a limit, and the limit is -1. So I'll say, because the limit as x approaches -1 from the left is equal to the limit as x approaches -1 from the right equals -1. The left-hand limit and the right-hand limit are both equal to -1. So the limit as x approaches -1 of that function is -1. I'm writing it this way because this is the way that we're going to have to write it next year in calculus proofs. I'm going to have to say the left-hand limit and the right-hand limit, I investigated them both, they equaled -1, so the actual limit equals -1. All right, give this one a try as well, this whiteboard problem. Notice that we're using the same function as we did up here, but now I want you to take the limit as x approaches 0. Do you notice in this case that 0 is not the place where I jump from piece to piece? So 0 is on, let's see, 0 is less than -1. 0 is in this piece, and it's not the jumping point from one piece to the next. It's just literally on this piece. That piece is just a horizontal line, a constant -1, right? So the limit as x approaches 0 of f of x is just -1. So if it's solidly on that piece, this x value that we're investigating, it's solidly on this piece, not on the jumping point, then the value is just plug that x value into this piece of the function. Okay? All right, so here's your assignment. There are 10 problems. It looks like more than it is because a lot of these will be just direct substitution. The number of problems where you actually have to really dig in there and do some work is only just a couple of them. Okay, so the next time we're together, we'll talk about 11.3. That's our last lesson of new material. We'll talk about continuity. See you then.